Every time you wake up your phone, you are looking into a piece of glass that looks back. Behind that small, darkened strip at the top of your screen lies a sensor array waiting for your exact physical signature. For years, proving who you were required pressing a tactile button. When that hardware vanished, in favor of smooth glass, the phone had to find another way to verify your identity. The solution was to hide a microscopic engine inside that notch. In a fraction of a second, it fires a highly structured grid of exactly 30,000 distinct invisible infrared beams to map the topography of your face. Packing tens of thousands of coherent light sources into a space this small required replacing the horizontal orientation of traditional lasers with a design that could fire straight up. Traditionally, lasers fired sideways. They were built as horizontal structures that emitted light out of the thin edge of a semiconductor wafer. Because of this sideways geometry, manufacturing them was incredibly fragile. Technicians literally had to take diamond saws and manually cut the wafers into individual microscopic blocks to expose those emitting facets. Leaving the emitting edge exposed created a fatal structural flaw. As the intense, focused optical energy passed through that tiny cleaved edge, localized heat would build up until the facet would literally melt itself, a failure known as catastrophic optical damage. Beyond the physical fragility, a horizontal footprint simply takes up too much space. You cannot fit 30,000 sideways firing lasers onto a single millimeter-wide chip inside a mobile device. To make facial biometrics possible, engineers had to force the light to shoot straight up from the surface of the chip itself. In 1977, Japanese researcher Kenichi Iga proposed a vertical cavity design. The scientific community dismissed the idea because abandoning the horizontal standard seemed physically impossible. The earliest vertical prototypes immediately hit a massive thermal barrier. The metallic mirrors they used trapped immense electrical resistance, generating so much heat that the devices would burn out the moment they were turned on. To keep his first working prototypes from melting, Ilika had to submerge the entire testing apparatus in liquid nitrogen. Operating at negative 196 degrees Celsius, or 77 Kelvin, kept the laser alive just long enough to prove the physics worked, but it was completely useless for consumer electronics. If this technology was going to survive outside of a frozen laboratory, engineers had to abandon metallic mirrors entirely and solve the thermal problem at the atomic level. Instead of metal, they built distributed Bragg reflectors. Stacking alternating crystalline layers creates an optical maze where light builds intensity. Every layer must be exactly 1/4 of the laser's wavelength. If off by a single nanometer, light falls out of phase, ruining the wafer. To achieve this sub-nanometer tolerance, manufacturers use a precise gas deposition process. They flow molecular vapor over a surface, growing crystalline mirrors atom by atom. Managing the heat generation eventually required a specific chemical interaction. Engineers introduced a layer of high aluminum alloy and exposed it to superheated steam. This steam selectively rusted the outer edges of the aluminum, leaving a tiny non-conductive aperture in the center. This oxide funnel forces all the electrical current directly into the middle of the laser, lowering the threshold current enough to run efficiently at room temperature. That atomic-level precision, paired with that microscopic ring of rust, is the reason 30,000 lasers safely operate millimeters from your eyes. By late 2017, Apple faced a critical logistics bottleneck. They had designed a smartphone dependent on these vertical lasers, requiring the global supply chain to scale up production by 1,000% to meet the demand of a single product launch. To secure their components, Apple invested $390 million to retrofit a decommissioned factory in Sherman, Texas, dedicating it entirely to vertical laser production. The challenge was immense. They had to maintain strict nanometer-perfect tolerances while running wafers through massive automated cleanrooms at the unrelenting pace of global consumer manufacturing. Modern biometric security became a reality because they figured out how to take an incredibly sensitive laboratory process and perfectly replicate it millions of times a month. The successful scale-up of the Sherman plant proved that the region's local workforce and infrastructure could manage the extreme metrology required for high-volume semiconductor growth. This established a localized hub of expertise that laid the groundwork for further investment. Today, that city is home to a $60 billion expansion, a massive multi-fab complex built to manufacture the foundational analog chips that manage power and signals for nearly every modern device. The technology required to map your face was once considered a physical impossibility, capable of surviving only in a bath of liquid nitrogen. Through decades of isolated research and extreme material science, engineers bent light to their will. The vertical laser stands as a microscopic solution to a massive engineering problem, quietly doing its job every single time you look at your screen.